So let's begin today's session. In chemical engineering, we use reactors that we produce to get products, and the product that you are going to get can be in different kind of phases. So the phase that the product can be in a heterogeneous phase, that will be, or a homogeneous phase. So when you get this phase, we want to achieve purity of each component that's in the product that has been produced. So there is a need for separation. So that's the need for us to do separations today. And as we have learned how to use reactors to produce products, today we are going to learn how to use the separation equipment in ASPEN to do separation. So that brings us to today's topic, separation equipment. Separation equipment. So I'll move direct as our time. We have already spent 15 minutes. Then we go. So as I explained to you, in chemical process, you see that you have a reactor that's going to produce your product for you. So the feed, whatever is coming into the reactor, you get your products, and the product can be in any phase. So it can be a heterogeneous mixture. So if your product is a heterogeneous mixture, it has to go through this first stage of separation. That will be physical. So here we will separate solids from the liquid or gaseous phase. Then from this side, we come to, you are having a homogeneous phase mixture. Then you use separation. So here you can use some equipment like cyclone. You can use sieve to do your separation. Then you get a homogeneous phase. Then you use a separation process. That can be, you can use distillation, evaporation, absorption, extraction. So all these things can be done to get your desired products. And thank God, ASPEN have particular models that can be used to do separation. So I'll quickly switch to the simulation window. Let me expand it a bit. Okay. So you can see we have separators here. We have columns here. So when we come to separators, ASPEN have models that can be used to do separation for you. So this flash 2 is used to separate a homogeneous mixture which is in vapor liquid phase. So can do separation for you in vapor liquid phase. Then for the 3-1, can get 3 outlets, and it can be used as a flash drum which can work in vapor liquid separation. So for example, you have a vapor, a gaseous something. For example, let me say you have methane, which is in mixture of water and gasoline. So you can use this to do the separation so that the vapor one will go to the vapor phase, and the water and the gasoline will also separate to different streams. So you can use this for vapor liquid separation. And this is a decanter that's used for liquid separation. Liquid separation. So you can't use decanter for vapor. Yes, you don't use decanter for vapor. And this is a separator that can be used to separate any components at all by you giving it the ratio that needs to be separated to that part. Okay, and this one too is a separator. Or you can click down to check the other ones. So if I'm using this separator to do my separation, I can change the icon to this part. Then I'll be using it. Right, so that's just by the way, that's how it is. So today I'll pick one of these, that will be flash 2, to do a simulation for you, all of us, to see how we can go about it. Then the rest, you once you know how to specify this, you will also know how to specify the others. And if you have problems, contact me. Then we'll move to columns, the distillation columns. So we have several distillation models here. We have DSTW and DISTL. So these two are shortcut methods, as in our outline. I illustrated that we are going to do shortcuts and a rigorous model. So DSTW and DIST. So this one, it works under the principle of Underwood and Gillian method. So you can use it to predict the optimal distillation column parameters. Then you use that one as a pre-step for one of the rigorous models. So we are going to use today, I'll show you how you can use DSTW to estimate and design parameters of distillation column, and later on we will use the estimated values to do a more rigorous model. Yes, if we have more time, we are going to dive into designing even the column internals and choosing um, the type of packings that are in the column. We have more time. So that's DSTW. So the same thing applies to DIST. So this is RADFRAC. So RADFRAC is a very powerful model in ASPEN, which can be used to do model distillation. It can be used to model absorption on a lot. So these are the models of RADFRAC. So you can use RADFRAC, this type of RADFRAC, which will be used for absorption. It can be used for this, a stripping column which has a reboiler. And you can also use it for a rectification column as well. So RADFRAC is very powerful. That's what we are going to use. And this is extraction, multifrac, petrofrac, and concept. So this is what we are going to do. And again, we are going to learn it by using a problem. So quickly, I'll go to line tab. All right. So today, the first problem that we are going to do, we are going to see how we are going to use ASPEN Plus to separate styrene and ethyl benzene. So there is the problem. The styrene production is made using ethyl benzene that is at 110 degree Fahrenheit and atmospheric pressure. The mass composition of the stream is shown in the table. That is ethyl benzene, styrene, and lectadecane, and you can see the fractions there. The required distillation column operation conditions shall be determined. That's distillate flow rate, reflux ratio, number of stages. The goal is to recover 99.2% of the ethyl benzene by the column top using a molar reflux rate of 6. The styrene recovery percentage is of 2.5%, taking a pressure at the top of 45 torr and in the bottom to be 105 torr. Consider the use of a total condenser, and a property method has been suggested to us as Penn Robinson. We should use Penn Robinson. So this is our problem. Now we are supposed to open a new ASPEN Plus case and enter the chemical components and select the property method. Then we continue from there. I'll switch to the property environment and look for heptadecane. Okay, so let me go to find search for ethyl benzene for the first. Ethyl benzene. I'll narrow it to equals. Find now. Okay, so ethyl benzene is here. All right, so ethyl benzene, I'll add it. Then I'll look for the other one. The next one is styrene. Okay, styrene is here. I'll add it. Then the next one is heptadecane. Right, and heptadecane. I'll add that one too. Then I'll go to next. Look for Pen Robinson. So I told you can just scroll down. You can just start typing something. The Pen Robinson. So I'll start PEN. Then Pen Rob will come. So once I have Pen Robinson, I go to next again and run. Okay, so my table has been generated. So I can begin to do my work. So I go to next, everything is complete. I switch simulation environment. Now before I start, let me go and give the setup title. Oh, today is Bootcamp day 6. Bootcamp 6. And the description, I'll copy the problem here. Copy the problem. Copy the problem and paste it. Okay. I'll paste it. And that's okay. Now let me move to the environment. So now I have to specify my inlet stream. So I will start. I'll name it feed. And before I go on and put anything there, I told you we are going to use two. The first one, we are going to use DSTWU to find the design parameters, and later on we use the rigorous one, which is radflag. So to do that, it means I need the same feed to be duplicated. So I'll go to the duplicator, manipulator, and choose duplicates. I'll put it here and name it do p do -1. Right. Then I'll connect my streams to it. So I'll move it up. Yes, I'll name it f-1 as feed 1. Then I'll bring this one down, give it a name as f-2. So once I'm done, I connect the feed stream to the duplicator. Then I go to next to specify the feed stream. Yes, so in the problem, says that ethyl benzene is at 110 Fahrenheit and 1 atm. So go ahead and specify the stream 0110. Then I'll change this to F. And this one is 1 atm. Okay. All right. So now go ahead and specify the composition site. Go to mole fraction. All right. Let me come to my side. Okay, everything is straight. Let me copy everything, the cells, and paste. All right, so unfortunately I have gotten an error. So use it. Okay, that means my file can crash at any time. So people, we will need to pause this till I get back to be able to restore it. So I'm going to pause the recording. Okay, so you come to tau benzene, put it there. This is mole mass fraction. I guess the question is mass fraction. The mass fraction, okay, not mole fraction. So I'll copy styrene and I'll go to the where styrene. Then I'll come to this side, copy everything, send it to spin. You see the amount of feed that was given. Okay, the feed flow rate was not given. All right, where is that? Okay, so the feed flow rate is supposed to be 27,550 pounds per hour. So 27,550 is a mass pound per hour. Okay, and this is done. Yeah. Okay, so I can run it. Okay, so now my resource is available. I have duplicated the feed. So now that we have this, we move on to the columns. So we are going to use a shortcut called DSTWU. So you put it here, you give it a name, DSTWU. Let me enlarge it a bit, bring it here. Then I connect the feed to the column, connect it here, and I give the outlet streams. So this one, I'm going to call it distillate 1. Bottom product 1. Since we are going to use the same thing for the other one, product 1. Okay. Or if you have gotten up to this part, we are moving to where we are going to specify the DSTWU. So you come here. So assuming we were not given the reflux ratio that we are supposed to use and we are just supposed to do it, what you would have done is to put anything here and it is going to calculate anything higher here. For example, 30 reflux ratio or something, so that it is going to calculate the minimum reflux ratio for you. Then you can multiply it by the fraction that can give you an actual reflux ratio. So because we were given, I'm going to just type what was given to us to be 6. Then I'll come to the specification of the key components. So these are the key recoveries. So what do you want to expect? Which one is the light key? Light key is a component that you want it to live at the distillate stream, the upstream. So I'll select the light key to be ethyl benzene. Then it was given to us that we want to achieve 99.2. The problem, yes, 99.2. So we just change it to fraction as 0.992. Then you come to the heavy key. Our heavy key is going to be the styrene, which is 0.025. So you can define the lightest key to be the heaviest component that's supposed to live in the distillate stream. And you can define the heavy key to be the lightest component that's supposed to live at the bottom stream. So you have to understand this heavy stream. We want to recover more of styrene at the bottom, but just check. You will see that for here, the definition for this part is the recovery of the key component in distillate stream, or key component in distillate stream, that's the heavy one divided by the light. So if we want to recover 97.5 of styrene, we are not going to type 97.5, but we are going to type 100 minus 97.5, which will be 2.5. That's what we are going to write there. So the light key, this one represents the amount of heavy that we want it to be in the light or the distillate stream. That's it. So let's specify the pressure as well. The pressure says the condenser is 45 and it's in torr. Then the reboiler is 105, same thing in torr. Says we should use the condenser, total condenser. So we are supposed to note something. So come to calculation, check in, generate table of content, reflux ratio versus number of theoretical stages. And I'll explain that one to you. So what you have to note is that higher reflux ratio, the column has to have higher liquid load. Once the reflux ratio is high, there will be high liquid load and the column diameter will increase. And as the column diameter increases, you will see that the energy duty for both condenser and reboiler needs to increase for we to achieve our desired separation. And once that one is increasing, it means that the cost that we are supposed to incur during the operation of the column needs to go up. So as reflux ratio increases, you will see that the operating cost will increase. But the initial cost, which is the capital cost that we will need to install the thing, will be low. So you will get it very well. So let me generate 50 points so that we will compare the good, or optimal reflux ratio and number of theoretical stages that we should use during that. So if you have been able to specify everything here, let's run it to see the result that will be given. So the results have been generated without errors. So I'll go here. I'll come to this, click on it, go to stream results. All right, so now we can see that there is a separation. A separation is done. You can see the mass flows that we are using. So you will see that there is the feed that we are having. And let me go to mass fraction. There is the amount that came in. So at the bottom level, you are seeing that we have more of styrene, which is close to almost 99% of the bottom product as styrene, and we are having the distillate stream to be 98% of it to be ethyl benzene. That's that. So we have been able to separate the two, and you can see that at ethyl benzene there's no heptadecane because it is heavier. All of them are in the bottom stream. That's for the shortcut method, which is DSTW. So let's see the results that shortcut method can give us. So select it like this, right click and go to results. So when you come to results, you will see that we have reflux ratio, minimum reflux ratio given to be 4.15, 4.15 or 4.16, and the actual that we use is 6. And the minimum number of stages is 26. And we have the actual number of stages to be 43. The feed stage is 19.1, and the number of actual stages above the feed is this. So you can see that the reboiler duty, let me change the unit to kilowatt, is 5,523.3 kilowatts. And you will see the condenser to as 5,386.79. So these are that, and this is given feed distillate to feed ratio. So these are the stuff that we are going to use to model the. So these are the ones that we are going to use to model the rigorous model. So now I made us to check in a reflux ratio versus theoretical number of stages data. And now you can see that this data is here. So you will see that we have at when we want to use 27 number of stages. So 27 number of stages for this separation. It means it is good for us to use a reflux ratio of 44.25 for you to achieve the same separation. And once we go down, we use 49 number of stages, we can use 4.98. So let me try and generate a graph for this. So I'll go to custom. Okay, theoretical versus this. All right, so you can see that it goes like that. So this is the reflux ratio, and this is the number of stages. So you can see here, when we have a number of stages to be 50, let me take 50, you can see that the reflux ratio is 4.9. So how is this important? That's what I was trying to explain earlier, that as the reflux ratio increases, you see that the number of liquid that will be in the distillation column will be higher, since we are recycling more of the distillate stream back to the column. So it will require a larger diameter, and hence we will see that the energy duty for both condenser and reboiler needs to be increased. And as those one increases, you see that the number of stages needs to come down. The number of stages will go down, and that will lead to increase in operation cost, but it will be reducing individual investment costs, which will be the capital cost. But if we are using low reflux ratio, when we are using low reflux ratio, this is what happens. It means more number of stages is needed. So you can see, as the reflux ratio decreases, you see that the number of stages also increases. So as those one happen, you will see that the diameter of the reactor will decrease. So a caution for the people that will be designing their plant, you will just increase the number of stages maybe to 105 stages, and your diameter will be something like, so that will be a tall column, and your diameter will be, maybe you are saying it is 0.5. That one will be like a cane, and just little environmental interference, something like air is blown, you see that your column will just be falling down. So let us take good care of this. So once we have been able to do this, and we know that I'm not going to take anything from that, I'm going to use the summary results here to model the RADFRAC, which is a rigorous model for you to identify the stuff that we can do. There are more that can be done in RADFRAC, for example, designing column internals. If you are getting this error, then check your distillation column and how you specify them. Remember what we are using? We were using different units, and the unit for the pressure was torr. So check that one and let me see feedback from you. So next one is, can you please go over the explanation of the results and the reflux ratio profile? Okay. Um, so let me quickly do that. So you have this one. So let me draw the graph again and explain.
Hello, Clinton. We can't. I can't see your screen. I don't know if the others can see your screen.
I haven't shared my screen. Let me share my screen soon. Okay. So what I was saying is that, let's look at how the graph goes. So you will see that the reflux ratio, as it decreases, the number of stages increases. Yes. And the explanation is that once the reflux ratio is high, it means that more liquid is being recycled back into the column. And that means you should have a column diameter which is large. So if the reflux ratio increase, column diameter will increase. And in a sense, the condenser duty that needs to cool the product in the distillate stream to send back to the reflux tank, to the column, the duty has to be higher. And the reboiler duties will also increase, since more liquid is being dropped into it, more will go to the bottom and needs to be reboiled and back into the column. So as that goes on, you will see that the operation cost will increase, because it will cost you electricity or the utility that you are using for the cooling and the heating. So the operation cost will increase, and the operation cost will increase, but the cost for installing the column that one will decrease, since you'll be using higher reflux ratio and a lower number of stages for your column. On the other hand, when you are using a low reflux ratio and many more stages, many more stages are required to accomplish the same desired separation. And hence you will see that the diameter and the energy duties will diminish, or it will decrease. And the operational cost will also be low, since there will not be there will not be more energy needed to do cooling and heating. And you will see that the operation cost will be low, but the cost for installing the number of stages, if the stages is a tray, the cost to install the trays in the distillation column, that will be higher. If it's a packing, the cost to pack the column will be higher. So once you are okay, let's move to our main flow sheet and choose rad frac. So at the end, we are going to compare the separation efficiency of the two. Rad frac. So choose rad frac, put it here, give it a name. So I'll name it as it is, rad frac. Then I'll just expand it a bit. So I'll put the rad frac here. Okay. Then I'll reconnect my F2. So this one, I connect it here. Then I'll join, okay, this one. Let me give it a name as D-2. Let me bring my, okay. Then I'll bring this one here as B-2. Okay. So let me highlight everything and align them. Okay. Let me bring it here a bit. E2. Right. So now that we are done with this, let's try to specify the column. So go to next, or you can just double click on the column model to specify it. So let me go to next. All right, so next. So you see that there's a calculation type here. So you can do a rate based, which is a dynamic distillation, and equilibrium. So we are going to choose equilibrium. Then the number of stages, you will just come to the results, of the DSTW. Okay, no, where is it? DSTW results. So you will see that the number of stages that we are going to use, the actual number of stages for the separation, the result that we have is 42.6. So we can't just select 42.6 and put it there. A fractional, so it means that other stage will be a fraction. No. So we are going to select a stage that's higher than, we are higher than 42.6, which is the immediate one. So we are going to choose 43. Number of stages, so rad frac, here we choose 43. Now for the condenser, we are choosing a total type. The reboiler, we are using a kettle reboiler. Then the phases, we are leaving it at vapor, liquid. Then convergence, we are using it as standard. If your distillation is cryogenic, you choose cryogenic. Azeotropic, you choose that. Petroleum or wide boiling, you choose that. So now we come to distillate rate and this part. So operating specification, I already told you that DSTW is used to get operating conditions for the optimal one, for the rigorous model. So the reflux ratio that we are using is 6. So the actual reflux ratio is 6. All right, so now let's move on. So here I'm going to choose reflux distillate rate. So the distillate rate will be the flow of the flow of the your lightest key that you want it to be in the distillate stream. So you can just type, go to the feed section and see the corresponding rate that's equivalent to the ethyl benzene. Or better still, we can choose something different. So I'll just come to rad frac, go to the results and look at something that was given to us. So you can see that we have distillate to feed ratio that was given to be this. So I'm just going to copy it as in Control C for the distillate to feed. Then I'll just come to rad frac specification and look for distillate to feed ratio. So you have distillate to feed ratio and I'll just do Control V. So that you see that the configuration part now, that one has been confirmed. Internal has been activated, but we will not do that for now. We will move on to the streams and do that. So you come to the feed stream, you will see that it will ask you where is your feed stage, what the location of the feed stream. So which stage? So you see that here is 19. So we are going to choose the feed stage is 19. So we are going to choose 19, not 19.14, or we are going to choose 20. So if we are choosing 19 because it is the 19.14, it should be at above the 19 stage. So 19 and it's above 19 stage. If you choose on stage 19, it means it will just pour on the stage. So if you choose 19 stage above 19, it means it will pour from maybe 20th stage or that. All right. Then once you are done with that, for the this side product streams, ASPEN will do it for you. If you want to do pump arounds and other ones, then you go ahead and do that. So let's go to pressure, the pressure. So we are using the same pressure conditions as in the that of. So the stream, you just put it at above 19. Let's go to this side. The pressure. So we are going to do, it starts from 45 torr. And when you specify 45 torr, it's enough. Aspen will just do it like the condenser pressure and just move. But we can see that the column pressure drop was available. So what we are going to do is that I'm going to specify all the other ones so that it will just fit that of GSTW. So that it will fit that. So I'm going to specify this side to be 50. So 50 up to this side, I'll choose this side to be column pressure drop, not stage, column pressure drop to be 55. So from this side to this will be 105. The column pressure drop, that will be 105. Okay. Yes. So once you are done with this, you can,
Say,
yes.
you need to change the unit for the of pressure for the stage 2 and the last one. Oh, okay.
So once you are done with it like this, you can run. So as we wait, all right. So my results is available. Let's check the results.
Clinton, sorry. Please,
Lisa, I can hear. Hello.
the condense. Yeah, I want to confirm the condenser was from the configuration, whether you chose total,
So
partial,
so we are doing just as the other one. So that's we are using total.
total. Okay.
So Mr. Henkra is tall. Okay. So how many of us have been able to run it to get results? Please, if you have
I had
result, all right. Please talk.
when I ran it, I had error. So
Had an error.
yes,
Okay.
all calculations were completed with errors.
Okay.
All right. Okay, I'm coming. We will resolve that. Does anybody
Eh,
have another question?
Yes. Please, the number of stages, did you round it up from
Yes.
the 19? Okay.
Okay. Please, who had the results? All right. So those who are getting errors
Okay. I have results.
have results. Okay. So those who are getting errors, I guess, come to this side again. The number of stages is 43. Condenser total leave everything as it is as before. Then here, the reflux ratio is 6, but it was at first at distillate rate. Change it to distillate to feed ratio. And when you change it to that part, just come to the DSTW and look for distillate to feed ratio. Just select it, copy it with Ctrl C, and come to the specification, put it there. And when you are done with that, move to the stream. The feed stage should be 19 and the convention should be above the stage 19. So don't do anything for the product stream side, just leave it as it is. Then come to pressure. So for the pressure, condenser pressure should be 45. The stage 2 should be 50. Then you come to pressure drop for the rest of the column. For the rest of the column, that's 55. So you see, this is 50. So for the rest of the column, that means from stage 3 up to stage 43, the 40th column, the pressure drop is going to be 55. So in addition, it means the reboiler side is going to be 105 tall, just as that in the DSTW. Please try that and let me see if you have results.
And from my DSTU results, my number of stages were 38 point something. So when I was specifying the rad frac, I used 39 for the number of stages. And my distillate to feed ratio was 0.75 something. So I used that one.
Your distillate to feed, all right. So
Yes.
just try it and let's see. Do you still have error?
Yes, that's what I used, and then I had the error.
Which version are you using? If you followed everything, you are supposed to get the same thing.
I'm using version 10.
Oh, okay. What property method did you use?
The parallel.
All right. So
Yeah.
let me. Okay, it's fine. I'm coming. Uh, Perpetua, have you seen any error? Have you tried to redo it? Okay. So Kojo, it worked for you. So those who are having errors, warning: feed pressure is lower than stage pressure. Please check the unit of your pressure in the. Okay. Thank you for the feedback. Dugan, check the unit of your pressure in the stage specification, in the column specification. Let me know the feedback afterwards. All right. So let me continue from here. So now we want to check the. Please, if you have problem, just stop me. Now we want to check the results for all of them. So go to stream, then click on boundaries so that it will just give us the boundaries results. Okay, so you see that this is the feed and these are the boundaries. So now let's compare the efficiency of the DSTW. So B1 is for bottom one, that's for DSTW, and that of B2 is for rad frac. So let's go to mass fraction. Mass fraction. So let's see. The bottom product for the DSW is 98, close to 99%. That's for the bottom. And this one is 98%. All right. But when you come to the distillate, all right. So it looks like we are getting the DSTW is getting more separation than the more separation than the rad frac, which is the rigorous one. All right, so let's check. All right. Okay, same everywhere. So it means we have to check the specification again. Okay. So now let me try to change the feed state to 20 and let me run it and see what I would get. Okay. 20. Okay. Or looks like it's the same. So when we are using the rad frac, the separation that we are getting, this is what we are getting. So we can go to the rad frac to see other results. Rad frac, I just go to results. All right, and you see that you have condenser duty given here, and that of the bottom boiler performance also has been given here. That's the boil up ratio and bottom to feed ratio. All of them has been given. Okay, go to. All right, so let's come to profile. You can check the profile, composition profile for the rad frac. So this is a rigorous one. So you can see it is here. So we can do a plot for that. Let me go to composition profile. Okay, for all the components. All right, so you can see that as stage 1, the blue is for ethyl benzene. As stage 1, the mole fraction of ethyl benzene is 1. It's 1, and at stage 1, the mole fraction of the styrene is 0. So at the first stage, you will see that the mole fraction of this is this. So as it increases, so this is the bottom part. At the bottom stage, you will see that we have less ethyl benzene within it. So that is the composition, and you can see that at stage 1, you will see that of the N-heptane is the same for all the stages. So most all of them are in the bottom products because that's the heaviest among the 3. So at this point, that's where the same thing, we are having the same separation. This is the stage 23.5 there. That's between 23 and 24. That's the composition curve for the component that we just separated. So that's it for rad frac. Let's move on to the setup again. And I'm going to show you how you can use rad frac to do internal specification. So when I talk about internal, I'm talking about the type of tray column that you are going to use. So just select the internals, and it will ask you if you want to generate internals. So you click on generate. All right. So now here you see that you haven't done anything for that. So to do that, what we do is you just add new column description. So this is column 1. The number of stages starting from stage 1 up to our last stage. The number of stages, okay, stage 2. The reason why I had an error is that stage 1 is where we have the condenser. Okay, so up to where we have the boiler. So all of them, those are not parts of the ones that we are going to design. Okay, so we have up to 42nd. All right, you can see that everything has changed. Now The mode is interacting sizing. You can change it to rating. So we have type of internal. This is a trade type. You can choose a pack column one, and the tray type that we are using is a sieve tray. It's a sieve tray or bubble cap. You can change it to what? So I'm going to leave it as sieve tray. The number of passes to be 1. ASPEN have suggested to us the diameter to be 4 meters, and that of the packing height. The distance between the packing is to be 0.6. The stage is different from the other by 0.6 meters. So now that you have this, you can try to view whatever is happening within your condenser. So your distillation column. So you can see them here. Let me go to view details. All right. So you will see that this is your tray. This is the tray. This is the tray that we are using. And okay, let me see the design parameters of the tray. So these are the design parameters for the tray. And the calculation methods, we are the jet flood and the reap. So those who are going to design distillation in final year, this will be a benefit for you so that you can visualize it. All right, so the sieve geometry is here, the diameter is given, tray spacing is here, then the holding, all of them is available for you. So this is that, and we can view. All right, so now this is the tray type. So this is our column, a stage view. If you are seeing the stage view of your distillation column per each stage, you will see that this is the feed stage. So you see the stage is coming, and if you look at it, you are seeing that the top column is here, this one is here. So this is the tray column. So something like a flat does it. Okay, so we have reaping, damping, wear, and all those stuff. That's operating points and everything. So I just wanted to show you that you can design a tray column. So that's that. So let me try and change this one to from a tray to packed before we will. Yes, so there is the pack column. So the difference between the packing height. So I'm going to give 0.01. All right. So once this is done, let's try to see the view. So you can come here, the type of packings. So you can use pour rings. You can use all the other stuff, ranchet and everything. Ranchet ring. I think we have ranchet ring in the unit operations lab 2. Yes, lab 2. Yeah, we have one of the columns is having ranchet within it. Okay, so let me choose ranchet, and let's view how ASPEN has designed it. Let's view that. All right, so design parameters. All right, so this is the packing, the stage view, how you are going to see it. So you can see the difference between how when you have packed it and when it is a tray column. So now we have packed from the first side down up to the 42nd stage. From stage 2 to this side have been packed with ranchet. So those who haven't seen ranchet before, you can pass by the unit operations lab and have a look at it. All right, so that's about column internals. So please, if you have any question, you can let me know so that we go on with the other one. Okay. All right, answer. I'm coming. Let me find the form. Please, how many of us were able to view the column internals? Okay, Kojo, Dugam. All right. So maybe if you are in, yes, sir. Amos, were you talking? All right. So if you have been able to do that, you can run the let's run to see the results. All right. I have my results to be available. I'm not going to. So you can even change the parameters here. So me, my run sheet, the run sheet that we have at the lab, I think is a ceramic. I think it's a plastic one. So you can choose it here to be ceramic or metal. Then you move on. All right. So now that we are done with this, you know the goal of this was to guide you to be able to specify distillation column, and I think we have been able to achieve that. We are going to do that for the flash column. So that at the end you will be able to know how to use different separators for your work. Sometimes if you are not able to use it for your design, just go to separator and separate the thing and you move. So I'm going to add another component. Okay,
Clinton,
yes, please
please solve the inputs to the rad track.
go
Can
on.
I? Yes, the precious. Did you for the third part? Was it the column pressure
About
gauge?
this.
Let me see. Yes. Okay, it was column. Okay. Yeah, I've seen it.
All right, thank you.
Yeah,
So
thank you.
I don't want us to um, create a new sheet for the problem 2, which is a flash and it's a simple work that we are going to do. So what I want you to do next is that the problem 2 says, let me read the problem 2. 100 kilomole per hour of a mixture. 100 kilomole per hour of a mixture containing 10, 20, 30, and 40% of propane, and butane, and pentane, and hexane respectively is preheated within a distillation column. The liquid mole fraction of the mixture is just 80%. Calculate the composition of both liquid and vapor phases and the temperature of the vapor liquid mixture at 700 kilopascal. Initial temperature of the mixture is 25 degrees Celsius and the pressure drop can property method and Robinson. Okay, so what we are going to do is just easier. So what I want you to do is to move to the property environment. Since we are using the same property method, just add the component that we're given so that we will do the other simulation behind what we have done. So I'm going to add heptane, uh, propane, another one up to that of H6. All right. So let's try to do that one very soon. All right. So the virtual, I'll do that. Let's try to finish this one. I'll do that after this. Wait, who's making noise? You must. All right. So try and give these names: propane, butane, pentane, and hexane. So I'll just name them. So propane is C3H8. Then that of butane, we are using the normal butane, so C4H10 isomer, the first one, dash 1. Then we go to the other one, which is C5H12 dash 1. Okay, then the next one is C6H14 dash 1. Then I'm going to give their names here as propane, of this to be butane, butane, go to N-heptane, that's pentane, hexane. So once you are done with that, you have to go to next. Yes, so property method has been taken. Yes, all right, so now we can run. All right, so everything is complete. You can do it like this. Then try to save it before it crashes, like just like my own crash. Okay. Then switch back to the simulation environment. Please, how many of us have been able to enter from propane up to butane? All right. Okay, do again. Please, can I know any other person who have been able to do it before we do the flashing? It's just a simple one. Okay, Janet. Oh, after today, you are getting error. Okay. Please, Kojo, which part are you getting the error? Is it at the property environment? Oh, you are not supposed to get error. You are not supposed to get error. Please, can you check it again? Check it again, the components that you used, everything, and rerun it. All right, thank you. Okay, so now let's go on to the flashing. So go to the simulation environment, find a space there. So you pick a new material stream. All right, let me give a name to it. That will be oh, these are gases. So gas feed, that's gas F. Then we are going to bring a flash column. So flash 2, the board. So flash. All right. Where is the name? Okay. So flash. Okay. So now you connect the streams. So here is for vapor stream. So this is vapor. Okay. This is liquid. Let's connect the stream. All right. So if you have been able to do it, let's specify the gas feed. The problem said the composition have more percent of 10 up to 40. So 10, 20, 30 of how we have arranged it. So you just look for it. Since we added them up, you can see that what we just added is the one from down up to this part. So you just give them, this is 0.1. The butane is 0.2, I guess. Check it again. Is 0.2. Pentane is 0.4, 0.3, and this one is 0.4. Okay. So now you can see the total mole fraction is 1. The problem was given the initial temperature to be 25, and it was given to us. The pressure wasn't given, but it was given to us that the feed was given to us that the liquid mole fraction of the mixture is 80%. So if pressure was not given to you, you can use this part, the vapor fraction part, to indicate it. So if liquid fraction is 80%, it means the molar fraction, the vapor fraction there should be 0.2. So indicate that as 0.2. Then we come to the flow. So in the problem, the flow that was given was 100 kilomole per hour. So you select 100 kilomole per hour. And once you are done with that, you see that the material stream has been specified. Material stream has been specified. Then go to main flow sheet once again. Main flow sheet once again. Now we are supposed to specify the flash tank, the flash column. So you come to flash. So the temperature of the column wasn't given to us. It wasn't given. So I'm going to assume that we are operating this at isobaric, adiabatic isobaric tank. Yeah, operation. So it's going to be adiabatic. So adiabatic, we choose duty for the temperature section, and we give it a duty to be 0. Since adiabatic, we don't add any heat to it, and nothing is removed. Then we come to pressure, and the pressure that was given was 700 kilopascal. So 700. Then kilopascal, so kp, kilopascal. That's done. So once you are done with this, you see that it will be okay. Required input is complete. Now we can, okay. All right. So now everything is okay. We have an adiabatic, isobaric adiabatic flash tank being fully specified. We can run to see the result that it will give us. So flashing will just separate it to vapor and liquid phase. Okay, so I wait as it work. All right, so now it is done. So it is done. It's done. And let me try to view the results. Stream results. Okay, so the gas feed that we are using was 100. All right. Now I'm getting the feed. All right. Okay. So it is not doing anything. If this thing is 0, what we are getting here is that none of them is vapor. None of them is vapor. Okay. Now let me check my feed composition again. I check this to be 0.4, 0.8, and at this temperature, none of them is vapor. All right. Okay. So that's okay. Okay, let me try and change it to 0.5. Later on, I'm going to show you, I'm going to give you a way to do sensitivity to find how much, at what pressure are we going to get the, all right. At what pressure are you going to get vapor fraction to be 0? You are going to do that. So now we can check extremes. Okay, so now you can see that it has been separated. And yes, so the pressure, so all of them are in liquid phase. all of them are in liquid phase. So what we are going to do is that the work that I'll give it to you is to perform sensitivity analysis on the block on the block pressure on the blood pressure. So you are going to be change the blood pressure from 100 kilopascal to 1000 kilopascal to see the vapor fraction that will be given. Uh, the vapor that will be present, the amount of vapor that will be present within the stream, because propane should be in vapor phase, but we are getting most of them to be liquid. So that's what I'm going to do. I'm going to give it to you to just to do, for me to check something, for me to see how you understood the vapor fraction work, the sensitivity work. All right. Please, if you have questions, let me know as our time is drawing. Uh, okay, if you have questions, let me know. Talk. Kwajo, please, any feedback? Have you been able to rerun it and get results? All right, thank you. There's any problem with the flashing? Okay, thank you. All right, so all right, so what we are going to do is that now we started from a mixer. Just we started from barrels minimum, like from nowhere, beginning level, and I know that now if you have been able to do from reactors, no, from mixers, you can specify property method. You can specify property method. You can also specify thermodynamic property. You can specify composition. You can draw flow diagram. Then you are no more a beginner in ASPEN Plus. You can do sensitivity. You can do design specification. You are no more a beginner.